Hi everyone, welcome to part 6 of chapter 8. In this section we're going to talk about problem solving. So now that we've talked about thinking, conceptualizing, and reasoning, now let's talk about how we solve problems. So problem solving goes through 4 different stages. So there's 4 stages of problem solving. And so there's a nice flow chart of these 4 stages on the right hand side here, where stage 1, then you interpret or frame and understand the problem. Stage 2 is where you generate hypotheses or possible solutions. Stage 3 is where you test the solutions, test those hypotheses, seek more to disconfirm one or the other. And then stage 4, you evaluate those results, and if necessary, you revise steps 1 to 3. So you'll notice that these 4 steps are very similar to the scientific method that we talked about way back in chapter 2. So that's kind of where the scientific process came from, is these 4 stages of normal problem solving. So you don't have to, not all your problems are going to be a scientific type of thing. It could be a problem of where you want to eat for dinner, something like that. But you will always go through these 4 stages, whether or not you you don't always consciously think about going through these stages, but this is what everyone does when they're trying to solve a problem. And how well we carry out each of these stages determines our success in solving the problem. So if we don't test, say, stage 3, if we don't test these solutions and hypotheses enough, then we might not come out with the correct solution. Or we might not, because we didn't test everything, we might not come up with the most successful resolution to our problem. So that's why these 4 stages are really important. Now here's just an example of a common problem that we talk about. This is the crow and trains problem, where you've got 2 trains traveling in opposite directions on different tracks. And so we say that we've got train A over here. He's traveling to St. Boniface at 25 kilometers an hour. 50 kilometers away, we've got another train traveling at 25 kilometers an hour as well, but it's headed toward Winnipeg. Now, if we've got a crow flying who's kind of weaving back and forth and coming down out of the sky at 60 kilometers an hour, at what point will the 2 trains hit the crow, right? So you're going to have to go through these 4 stages where interpret the problem. You need to generate some hypotheses or possible solutions. So maybe, writing down all the numbers and try to find, what equation would help you solve the problem. Stage 3, you test it out. You plug and chug. Stage 4 is where you come up with your answer and you choose what your best answer is. So this is just an example of a problem-solving problem that we'll use sometimes in experiments with participants to see how they problem solve. So the first step again is understanding or framing the problem. So when we talk about framing, what we're talking about is a mental representation. So optimal framing gives you a better chance for solutions. So the better you're able to represent the problem in your mind, better understand what the core problem is, the better chance you will have to find the best solution. Now, when we're generating solutions, we also want to talk about which procedures and explanations will be considered. as well as which solutions are consistent with observable evidence. So again, think about it with the scientific process. You can't draw a solution from non-existent evidence, right? So in order to correctly problem solve most efficiently, then you really need to make sure that you're generating solutions that actually fit the problem. Now, also when we're in step 1, then we also need to talk about the mental set. So this is our tendency to stick to solutions that have worked in the past. So rather than looking at every single solution possible equally, then what we tend to do is we're a little bit biased to past solutions. So, if you're locked out of the house, say, how do you solve that problem? Well, a lot of times, a mental set, a tendency for me would be to go to the neighbors and get a spare key. Later, then my parents did a hide a key, but I would still go to the neighbor's house for a key instead of using the hide a key because I had this mental set. I had this bias towards solving the problem the same way as I used to, even though there was a better solution now. Okay, so that's an example of a mental set. So being fixated with an approach, if it has been successful in the past, can be efficient, but it's not always going to be the best approach. So there's another common problem that we'll use to study how people do problem solving, and this is Luchin's water jugs problem. So in this problem, then participants are told you've got 3 jugs, okay? And this is the size of jug A is listed here, the size of jug B here, and C here. Now, so if A can hold, say, 21 liters, B can hold 127 liters, and C can hold 3 liters. Now, if you need to measure out 100 liters of water, how will you do that? Right? And so, what you may discover is a general problem-solving schema that fits all 7 problems, right? So for instance, in problem 1, then if you take, the B and you fill it up, you've got 127, and then you pour some into A, you'll be down to 126, and then fill up C twice, boom, now you've got 100 left in B. So you've measured out 100 liters, right? Now you can do the same kind of thing with all of the other examples here. So for number 6, for example, you can fill up A all the way and then pour it out once into C that holds 3, and you'll be left with 20, right? So that's an example. So you can see how you fill up one and then you pour out more until you're left with the correct amount in one of the jugs. And that's a solving problem. Now, some of these, that might not be the most efficient way of doing it, but it is a way to solve all the problems using the same mental set. And so it does work, it just might not be the most efficient. So we can do some step-by-step scripts for selecting information. And so these step-by-step scripts you'll develop with experience. So when we talk about an expert, then an expert may have many schemas for problem solving. We can also think back to if you talk about, say, chess. When you first learn chess, you don't have a lot of experience. And you might not know all the specific different types of plays you can do. But as you slowly develop your experience, you'll get more and more schemas for solving a problem of, the game. So an expert in chess will have a lot of these schemas kind of memorized already, so they can more quickly and more efficiently solve the problem presented to them in a game of chess. These problem-solving schemas can also help solve specialized classes of problems. So novices will rely on a general problem-solving method, which uses working memory versus long-term memory. So these experts are going to rely on their long-term memory, whereas a novice is going to use their working memory. They're going to kind of try to just work it out, whereas experts have these schemas already, so they're using their long-term memory. So they're able to use their working memory for other things. Now, there are different ways of solving problems, and one way to kind of figure out what's the best solution is to use an algorithm. So algorithms are formulas or procedures that automatically generate correct solutions. So algorithms, you really think of them as like a mathematical thing, but it can also be a chemical formula. So these are just formulas for kind of correctly picking the correct solution. Now, other than algorithms, there's also this thing called heuristics. And so these are general problem-solving strategies that we can apply to certain situations. So these are mental shortcuts, okay? So algorithms will solve a problem, whereas heuristics is a strategy we can use to speed up solving the solution, okay? So it's kind of, it's really just that mental shortcut. So here's an example of a means-end analysis, which is an example of a heuristic, okay? So in this task, you start here, you've got 3 discs, A, B, and C, different sizes, on peg 1. Now what you need to do is you need to move them to peg 3 in the same order. But as you're moving them, you could not put a bigger disc on top of a smaller disc. So example, if I put A on 2, B cannot go on top of it because B is larger than A. So how do we solve this problem? And what we can do is we can use a means-end analysis. So this will identify the differences between the present situation and the desired state, and then it will use a sub-goal analysis to reach the goal. So in other words, it's again a mathematical way of telling you how to solve it, of giving you tips and tricks on how to solve this. Now, you're not always going to have a clear solution. So sometimes you're going to have some uncertainty. You're going to have to do some decision making, and heuristics can play a role in this. So one type of heuristic would be a representativeness heuristic. So this heuristic says, what does it look like, seem like, and represent? Okay, so what does, that's where this representativeness heuristic comes in. So how closely something fits a prototype for a particular concept. This is used to determine, say, class membership. This is also like when they do polls before an election. That's kind of like a representative heuristic. They're taking a sample of the population that looks like the population, that seems like and represents the population, asking them the question, and then they're using the results of this. They're using the results of the prototype to determine how the entire population will respond. Okay? Now, sometimes there can be some illogical judgments. So not everything will fully make sense, right? So this graph shows the mean likelihood judgments made by participants on the bias of the description of Linda. Okay? So Linda is, for example, some people would say Linda is a feminist, or Linda is a bank teller. Linda is a bank teller and a feminist. Okay, so those are the three options. And then on this side here, we have the likelihood. Okay, so the highest likelihood would be closer to a 1, closer to the top, and a lower likelihood would be near 8. So overall, when presented with the two things that Linda's a feminist, Linda's a bank teller, or Linda's both, people judged it to be more likely that Linda's both a bank teller and a feminist than rather just a bank teller. And logically, being able to tell the difference between this is impossible. You know nothing about Linda. Linda's, really made up. But how can you judge these things based on just the name and saying these things? And logically, why would she be more likely to be both a bank teller and a feminist than just a bank teller? Right? So logically, that doesn't make sense. So this is what we call an illogical judgment. And this is something that, can happen, but it is, it's just not, it doesn't make sense. Now, there's other types of heuristics as well. So we've got an availability heuristic. So this is where your judgments and decisions are based on the availability of information in memory. In other words, you're more likely to use a heuristic or use a solution that you've used more previously in the past than one that you haven't used for like years. Why? Because the one you've used more recently is going to be more available in the memory, right? So kind of that use it or lose it. Because you've used it more recently, it has a stronger connection in the long-term memory. So it's going to be more available to be recalled and used. A problem is just because information is in the forefront of our memories doesn't mean it frequently happens. Okay? So just because it's more available doesn't always mean that it's the best approach. Also, just because something's more available in our memory doesn't mean we're actually going to recall it more, okay? So, availability heuristics is a thing, but it doesn't always happen. Now, when doing problem solving and using these heuristics, you of course have to talk about confirmation bias and overconfidence. So confirmation bias is where you look for evidence that will confirm your beliefs and not look for evidence that could disconfirm your beliefs. So rather than taking in all of the evidence presented, which if we look back here, that would be, really looking at stage 3, then we're not doing that because it wouldn't align with what we want the outcome to be, okay? So confirmation bias can be a problem when doing problem solving, as well as overconfidence. So this applies to others, both situations and ourselves. So you can be overconfident in other people, you can be overconfident in a situation, or overconfident in yourself. And by being overconfident, you can actually sway kind of stage 4 of evaluating and saying this will be the best solution, because when you were testing the solutions, you put too much confidence on a certain thing, and so your stage 4, your problem success is going to decrease because of this overconfidence. So here's an example of displaying overconfidency, okay? So overconfidence is illustrated in the discrepancy between the accuracy with which students predicted that a specific event would occur to them during the coming academic year and the degree of confidence they had in their predictions. And overall, what we saw was the accuracy was considerably lower than the confidence level, even for those events which the students expressed a complete certainty. So pretty much what we're saying is, on the y-axis here, this group of bars is for all predictions. So this could be, I'm going to get an A in all my classes, I'm going to, not skip a class, any type of thing, and the students predicted the likelihood of occurrence. And overall, all of their predictions was about 80% likelihood that this would occur. But what we actually saw is that it ended up being just below 70%. So they were overconfident in predicting what they'd be able to do throughout a term. Now over here on the right side, it's looking at only these predictions where the student said, I will 100% do it. Like 100%, I'm totally going to do it. Like, I'm never going to skip a class. I'm going to go to every single class, even if I'm sick. 100% confidence before the start of term. And by the end of the term, our actual accuracy was below 80%, about 85%. So again, you see how students are overconfident in themselves and in what's going to occur or what they'll be capable of throughout the term. Okay? Now, overconfidence isn't always a bad thing. It's fine to be, overconfident in yourself sometimes. We also need to be realistic sometimes, pretty much. Finally, when problem solving, you can also have what's called creative problem solving. So again, creativity is where you produce something new and valuable. So we see this a lot in, say, functional fixedness, where we're fixed in a perception of proper function of an object and blinded with new ways of using it. So functional fixedness prevents us from doing creative problem solving because we're not able to use our creativity. We're not able to produce something new and valuable because of functional fixedness. Now, with incubation, then this is where creative solutions pop into your mind. So different perspectives may have emerged, it may have different sets, and your biases will dissolve. So incubation is a good thing because it allows creative problem solving to occur. This is also where we get what's called divergent thinking, which is the generation of novel ideas. And these novel ideas or creative problem solving is what allows us to move on and, make the world a better place.